Okay, welcome to our seminar. Today we are very happy to have Hao Wu from Tsinghua University, and she will talk about crossing probabilities in 2D critical lattice model. Thanks, Hao.
Hello, everyone. It's my great honor to speak at a seminar so I'm not sure who are the organizers. So I think you three are the organizers. And today my talk is about crossing probabilities in 2D critical lattice models. So in this talk, it will relate to several works. And here is a list of my collaborators. Vincent Befaha is a researcher at CNRS in France. Jianding is a faculty at UPenn. Han Yong was my postdoc before, and now he is a faculty in Shenzhen University. Liu Mingcheng is my first PhD student. And Evelina is working at the University of Bonn, but now recently she moved to Helsinki. Matthew Worth was Jianding's PhD student. Now he's working at Facebook. Okay, so my talk will have three parts. The first part is about the classical Ising model, and it will give a background on what kind of problems we are interested. The second part is about crossing probabilities. The third part is about uniform spanning tree. So for the Ising model, we mean the most classical definition for the Ising model. So it is a model introduced 100 years ago by Lenz, and it is a model for ferromagnets. Lenz introduced it to understand the phase transition for the ferromagnets. Okay, so the definition for Ising model is very easy. Suppose we have a finite graph. At each vertex, we put a spin. The spin is either +1 or -1. And then we define the Hamiltonian or the energy. The Hamiltonian is defined like this. So for each neighboring pair of the vertices, we take the product of two spins, and then we sum over all edges, and we put a minus sign in front. So because the spins are either +1 or -1, so the product is either +1 or -1, indicating the two neighborings are agree with each other or disagree with each other. So in short speaking, the Hamiltonian is proportional to the number of disagreeing neighbors. So in other words, this Hamiltonian is characterizing how the chaotic system, how the disorder in this system. And the Ising model is a probability measure defined like this. For each spin configuration, it happens with probability for each spin configuration is proportional to the exponential minus beta times the Hamiltonian. And the beta is the inverse temperature in the physics meaning. After this model was introduced, so here is three pictures for the simulation of this model. And we see that when the temperature is very low, one of the spins will dominate the system. So this represents that with the ferromagnet has magnetization. As the temperature increase when the temperature is very high, we see that the two spins are mixed up. So here is the chaotic phase, and we don't observe magnetization anymore. Okay, so after this model was introduced, there are two natural questions. The first one is, what is beta C? So what is this critical temperature? This question was answered 20 years later after the model was introduced. So if we are talking about the Ising model on Z-square lattice, then the critical temperature is we are able to calculate what is the critical temperature. So this beta C is 1/2 times log 1 plus square root of 2. The second question is, what happens to this critical phase? We know that when the temperature is very low, we have ordered phase. And when the temperature is very high, we have chaotic phase. And what happens to the critical phase? In physics, there's a sentence something like if we are thinking about critical 2D critical Ising model, the system will become conformally invariant. But then the question is, what does it mean? How we understand what do we mean the system is conformally invariant? There are at least two ways to understand such conformal invariance. One way is to calculate the correlation function for the spin system. So suppose we pick endpoints in the domain, and we take the product of the n spins. We take the expectation, and after normalized properly, this correlation function will converge to a function in the z1 to zn variables. And this function is what we call the correlation function in the continuum. And this correlation function will become conformally covariant. So this is one way to understand what do we mean the system become conformally invariant. The second way to understand this conformal invariance is to look at the interface between the two spins. And this way of thinking gives us the notion of SLE process. So what is an SLE process? This is the critical phase we are interested in. And now we want to look at what is the law of the interface between the two colors. However, in this picture, the system is pretty complicated, and we see that there are interfaces going from a boundary point to a boundary point, and there is also interfaces in the middle form a loop. So in order to understand what do this interface do, we first simplify the question. The simplification is like this. So suppose we fix this rectangle, and we fix two boundary points A and B. We require all vertices on the boundary here to be minus, and all vertices on the boundary here are plus. And then from A to B, we can draw an interface. The rule to draw this interface is that we always keep the plus sign to the right-hand side of the curve and the minus sign to the left-hand side of the curve. And in this way, we can draw this red curve. So this is a curve going from A to B. Of course, there are sometimes come with indetermination, and when there is such determination, we can just choose to turn left. Okay, so after this rule is decided, we can draw uniquely an interface from this point A to point B. Here is a simulation for the interface in the critical Ising model. Okay, and then what is the conformal invariance? What does the conformal invariance mean? It means that if we take the scaling limit, this interface will converge to something conformal invariant. And the conclusion reads like this. The interface in critical Ising model on Z2 lattice with Diversion boundary condition. This is what do we mean by Diversion boundary condition? The interface will converge weakly to SLE3. So this is a random fractal process, and the index is a 3. So this 3 corresponds to Ising model. So far, there are in total 6 models proved to be conformally invariant. So here, let me summarize what are these 6 models. The first model is called loop erased random walk. It was proved that the scaling limit of loop erased random walk will converge to SLE2. The second one is the Ising model, the one that we just introduced. So the interface in the Ising model will converge to SLE3. The third one is the level line of Gaussian free field. It turns out that after normally define what do we mean by level line of Gaussian free field, the level lines turns out to be SLE4 process. The next one is called FK-Ising model. So in fact, this is a dual model to the Ising one. The next one is the Bernoulli percolation. So it was proved by Smirnov that if we consider the Bernoulli side percolation on triangular lattice, the interface will converge to SLE6. The last one is the uniform spanning tree. So in fact, this is a dual model to the loop erased random walk. So both of these models are conformally invariant and they are proved in the same paper. Okay, so this is the 6th model that so far we know that the conformal invariance holds. Okay, so then up to now is the background on the conformal invariance of 2D critical lattice models. And then what do we interested in this talk? So we're interested in the crossing probabilities. So here we go back to the Ising model. So in the previous slide, we talk about Ising model with Diversion boundary condition. Now we want to change the boundary condition. We go into a polygon with 6 marked points, say. So this 6 marked point will divide the boundary to 6 pieces of boundary arc. And now we require the boundary condition to be alternating. Precisely, we require it is all vertices on this boundary arc is plus, minus, plus, minus, plus, minus. So in this boundary condition, we see that there are going to be 3 interfaces. These 3 interfaces will connect among the 6 marked boundary points, and they form a planar link pattern. So when there are 6 marked points, we know that there are 5 possibilities of the link pattern. So here are the 5 possibilities of the picture, and above 5 pictures are 5 simulations. And now we are interested in the question is that what is the probability for each pattern to appear? So before I give the answer, let us guess what will happen in this picture. So in this picture, in the 5 possibilities, because I draw the points evenly spaced on the circle, and we may guess that this one will have the same probability. These 3 will have the same probability. And these 2 will have the same probability. And this all the 5 possibilities sum up to 1. So still we don't know what is the probability for each one, because we know that 3 times probability of this one plus 2 times of the probability this one is 1, but we still don't know what is the ratio between these 2 patterns. Okay, so this is a simple guess, and in this simple guess, we use the rotation symmetry of the model, and we will see if the 6 points are not evenly spaced on the circle, so they can be anything. So then it's not easy to guess what is the probability for each planar link pattern. Okay, so now let us go to what is give you the answer to this question. The answer is the following. So if we are thinking about critical Ising interfaces in a general polygon with 2 unmarked points, then we know that there are going to be n interfaces. These n interfaces connect among the 2 unmarked boundary points and give us a planar link pattern A, delta. And the answer is the following. So for each planar link pattern alpha, the possibility for this connectivity pattern to happen has a scaling limit. And the limit can be written like in the right-hand side. So the denominator is called Z-Ising, and the numerator is Z alpha. And here Z alpha is the one we call pure partition functions. Okay, so this is the answer, but I haven't told you what are the pure partition functions, so this is not a complete answer. So before I give the definition of pure partition functions, let me summarize what is the history of this formula. So in fact, in this formula, for the denominator, we already know that it has an explicit formula. It is a Fabian of between the 2 endpoints. So if after we map everything onto the upper half plane and 2 unmarked points become 2 unreal numbers, and then this denominator is just the Fabian between the 2 endpoints. So this formula was first conjectured in a paper by Bauer, Bernard, and Kitola in 2005. Later, Izurov proved a part of this formula, but he doesn't give the full description of all possibilities. And then finally, we solved it in 2008. And here we can also see that, in fact, both the denominator and the numerator are related to the correlation functions in conformal field theory. Okay, now I'm ready to give you the definition of pure partition functions. For what are these Z alpha? So Z alpha, by definition, it is a collection of smooth functions satisfying the following 3 properties. The first one is that it has to satisfy 2n PDEs. So this function has 2n variables, and we have 2n second order PDE. The second one is this function satisfies conformal covariance. Okay, so this conformal covariance is easy to expect because we already see from this formula that the limit of the probability should be a conformally invariant function. And we already have an explicit formula for the denominator. And for the numerator, we believe that it has to satisfy the same conformal covariance as the denominator. And the third property is called asymptotic. So this asymptotic comes from this fact. Suppose we are looking at these two boundary points. There is an interface connecting the two boundary points. And suppose these two boundary points gets closer and closer. And what do we expect? We would expect that this interface will disappear. So the 2 unmarked points will become 2 minus 2 marked points. And the connectivity pattern between n interfaces will become the connectivity pattern between n minus 1 curves interfaces. So for this asymptotic, just to describe this phenomenon. So suppose we have 2 marked points getting close to each other. After normalize this probability properly, we believe that this probability should converge to the corresponding probability for n minus 1 interfaces. Okay, so this is our definition of pure partition functions. But now question comes. Do we know whether their existence and the uniqueness of solution to such system of the definitions? Okay, the answer to these two questions is like follows. The first proved was the uniqueness. So Floch and Coulomb proved in 2015 that if we fix the parameter kappa between 0 and 8, then there exists a collection of smooth functions satisfies the required 3 properties. There exist and they are essentially unique. So by essential, I mean that we still need to add an extra weak control on the functions, but this is very weak. So basically, we can say that they are unique. Okay, this is the conclusion for the uniqueness. And then here is a summarize on the conclusion for the existence. For the existence, so first, Kitola and Peltola proved in 2016 that for irrational kappa, they construct the functions satisfying the 3 properties. And the tools they used in their construction is called Coulomb gas technique. Later, in a joint work with me and between me, Peltola, and Vincent Faha, we proved that for kappa between 0 and 4, we can also construct such functions. And the tool we use there is called global multiple SLEs. And in the third work by me, so I proved that we can extend this existence for kappa between 0 and 6. And there, the main tool we use is called hypergeometric function. So far, basically, we are happy because remember that we are interested in the 6 models and 5 of them are in this interval for kappa in this interval. So for at least this already gave a pretty good answer to this uniqueness and existence question. And precisely in the last work, we proved a conclusion like this. So for kappa between 0 and 6, we proved that there exists a unique collection of smooth functions satisfying the required 3 properties. And besides, we also proved that the function we constructed there also have 2 extra properties. There are 2 extra properties. One is that the function is positive. So in fact, this positivity is very important because remember that our goal is to relate this function to probabilities. So before we can prove that they are indeed probabilities, we have to know that they are indeed positive. Another property we proved is called a parallel bound. So here is the precise parallel bound. So we derive an upper bound for this collection of smooth functions. And this upper bound is very helpful because when we try to prove that the corresponding function give us the correct probability, we're going to use a martingale argument. And in order the argument to work, so we need some control on the martingale. And this upper bound will just give us this desired control. Okay, so this is the definition of pure partition functions. Now let us go back to this Ising model. Okay, so this is the previous page we have already seen. So in this question for the Ising model, we consider critical Ising model in a polygon with two unmarked boundary points. Then we have any interfaces. And these interfaces will connect among these two unmarked points and give us a planar link pattern. And for each possible planar link pattern, the probability is given by the C alpha over Z Ising. And this C alpha is the pure partition function we just defined before. Okay, so this is the story for the Ising model. And now we can ask, so far we already know that there are 6 models proved to be conformally invariant. And for the meta models, we can ask the same question. The first one is we can consider the multiple loopy raised random walk in the UFTs. So for this model, Carrella, Kitola, and Paolotola prove that the same formula holds, and we only need to replace the parameter kappa from 3 to kappa equals 2. This corresponds to the scaling limit of the loopy raised random walk. And for the Ising model, so this is just the story we described above. And for the level lines of Gaussian free fields, okay, so for this case, it is a little bit interesting because, so in fact, there are 2 versions of a discrete GFF. One version is the usual one we use. And for that one, we believe that the level line of the connectivity between the level lines of the Gaussian free field will converge to the corresponding formula for the continuum Gaussian free field. There's another version of the discrete GFF, which is called the metric graph GFF. And for that one, even though the metric graph GFF will converge to the same limit as the discrete GFF, but we prove in a joint work with Jian and Vers that and the material that, so in fact, in the metric graph GFF, if we think about crossing probability, this crossing probability is significantly different from the one for the continuum GFF. And in a later work with my students, we calculate explicitly what this crossing probability should be. And it turns out that those crossing probability in this case corresponds to solution to 3rd order PDEs. Okay, so this is the level line of the Gaussian free field. The next model is the multiple FK-Ising model interface. So for this one, this is a joint work in progress with Evelina and one of my students. So for this model, in fact, in physics, it is believed that the formula is no longer true. So in fact, we need a constant in front of each connectivity, in front of each pure partition functions. And this C alpha is also known to be explicit, but so far we haven't able to prove such formula to hold. And the next one is about multiple percolation interfaces. For this case, the same formula also holds, and we only need to change the parameter from kappa equals 3 to kappa equals 6. And the last one is about the uniform spanning tree. So now let me turn to the second part of my talk. What is special for the uniform spanning tree? So let us recall what I introduced for this pure partition function. So by definition, this is a collection of smooth functions that satisfies PDE, conformal covariance, and asymptotic. And I already summarized what happens to the existence and the uniqueness of such solutions. And here is the uniqueness conclusion. So Flaha and Kleban prove that the system, if the function exists, they are basically unique. But in their argument, they require that kappa has to be between 0 and 8. And here, 8 is not included. And for the existence, so here is a summary on the existence conclusion. So although we only know the existences for kappa between 0 and 6, and for kappa between 0 and 8 irrational ones, in fact, the existence is conjectured to be true for all kappa between 0 and 8. And here as well, 8 is not included. So this is the existence and the uniqueness of the pure partition functions. Then it is natural to ask what happens to kappa equals 8. So this kappa equals 8 corresponds to the model of the uniform spanning tree. So in order to understand this question, so what happens to kappa equals 8? The quick answer to this question is that when kappa equals 8, we can still calculate what is the probability of each of all the crossing probabilities in the uniform spanning tree, but the answer is no longer fitting the definition of the pure partition functions. So this setup is only designed for kappa between 0 and 8 is not included. So if we talk about what happens to kappa equals 8, this setup is no longer does no longer fit. Okay, so now what happens to kappa equals 8? In order to give a proper definition or meaningful definition for pure partition functions, we need to look at what happens to uniform spanning tree and what uniform spanning tree will give us the natural answer. So for uniform spanning tree, let me define this model quickly. So for suppose we have a finite connected graph. A tree is a subgraph of G without loops. And a spanning tree is a tree that covers all the vertices. And a uniform spanning tree, UST, is a tree that's chosen uniformly among all spanning trees. And in this talk, we focus on uniform spanning tree in topological polygons. And here is the first case considered for the uniform spanning tree in the setup. So in the uniform spanning tree, in the joint work between Lawler, Schramm and Werner in 2004, they proved that if we consider the uniform spanning tree in the Gaussian boundary condition, so the Gaussian boundary condition is very similar to what happens before. So we fix two boundary points A and B, and then we require this part of the boundary arc. All edges on this boundary arc belong to the tree. And for another part of the boundary arc, we don't require anything. Okay, and this is called the Gaussian boundary condition for the uniform spanning tree. And here in the picture is a sample for the uniform spanning tree in the Gaussian boundary condition. And there, we can introduce the piano curve going from A and up at B. So to draw this piano curve, we follow the rule that the piano curve stays between the primal tree and the dual tree. So this is a curve starting from A and end up at B. And in their joint work, they proved that this piano curve in uniform spanning tree with the Gaussian boundary condition converged to SLE8. And now we want to look at what happens to the uniform spanning tree in a general polygon. So here I draw an example with 6 marked points on the polygon. So I have 6, x1, x2, x3, x4, x5, and x6 for the boundary arcs between x1 and x2, x3 and 4, and 5 and 6. For those edges, I require them have to belong to the tree, and for the rest of the edges, I don't require anything. So this is a uniform spanning tree in a polygon with 6 marked points. And here we see that we can also draw the piano curve with the same as the same before. It starts from x1, ending somewhere. In this picture, it ends up at 6. and another curve starting from x2, and it goes somewhere. And in this case, it ends up at x3. And here is a curve starting from x4, and finally it ends up at x5. So here in this picture, we have 3 piano curves, and they connect between the 6 marked points and form a planar link pattern. And now we want to ask, what is the probability for each planar link pattern? And here is another example when there are 8 marked points on the boundary. So here for the uniform spanning tree, when we say that they are in a polygon, in fact, we can also put an external boundary condition outside of the polygon. So here like this, we already have this alternating boundary condition. So these boundary arcs are wired, but these wired boundary arcs can be further wired together in the outside. Okay, and now in this with this boundary condition, we consider the uniform spanning tree, and we look at what happens to the piano curves, how they connect between the 8 marked points. And it turns out that in this boundary condition, there are 4 possibilities as here. So the piano curve can go like this, can go like this. Okay, so with these boundary conditions, if we think about the piano curve and how they connect between the 8 marked points, there are going to be 4 possibilities. And now the question is how we encode the external boundary condition and the inside connectivity of this piano curves. So this comes to, so we want to encode this external boundary condition and the inside connectivity of the piano curves both by planar link patterns. So here we say that the boundary condition is beta, so it is a planar link pattern. So it gives us a pair partition between the 8 marked points from the outside. And for all the possible link patterns, we also mean that how the 4 piano curves connect between the 8 marked points. And it will also give us a planar link pattern. And here we say that in order for this two match up to be a tree, we require that the meander matrix between the 2 patterns, alpha and beta, has to be 1. Okay, so this is the restriction given by the tree, because we are thinking about a tree. Okay, so this is the uniform spanning tree in polygons. And now we can come to the question. So what is the uniform, if we consider the uniform spanning tree in a polygon with alternating boundary conditions, what is the connection probabilities for the piano curves? So the piano curves will form a planar link pattern. And for each possible planar link patterns, this probability is given by this formula in the right-hand side. So here, M alpha beta is the meander matrix that we introduced before. So this coefficient guarantee that the internal connectivities and the external boundary conditions give us a tree. And here later, we have Z alpha over F beta. The denominator F beta is called Coulomb gas integrals. And this Z alpha is the matrix, inverse matrix times this Coulomb gas integral. Okay, so this is the answer to this question. So if we are thinking about the uniform spanning tree in a polygon, and the connection probabilities for the piano curves inside will give us the probability will given by this formula. So this formula, so in this question, we are not the first person to think about this question. In fact, for this kind of probabilities, they were already calculated in a joint work between Kenyon and Wilson in 2011. So in their joint work, in fact, they consider what is the probability for the left-hand side, and they give a systematic way to calculate this probability. But the interesting thing is that, in fact, there's no way in fact, it is very difficult to see that the answer in their paper is the same as the answer in our paper in the right-hand side. Okay. So, and for this work, so in fact, the most difficult part is to figure out the proper observable for this uniform spanning tree in the polygon, so that the observable will give us all the answer for all possible boundary conditions. Okay, so now let me introduce what is this Coulomb gas integrals. So what are these denominators? So here is the definition of this Coulomb gas integral. So here, so first of all, beta is our boundary conditions. So this is a planar link pattern between the two unmarked points on the boundary. And then the Coulomb gas integral is defined like this. So it is a function on x1 to x2n. So first there's a product between these points. And then there's a big integral. The integrand here is a complex valued, it's a multi-valued integrand. So we can view all the variables u1 to un to be complex number. And the integrate domain is according to this boundary condition beta. Okay, and for this integrand, in order to very well define what do we mean by this integration, in fact, we need to choose a branch for the integrand. And we choose this integrand in the following way. We choose it to be real and positive when it is when this UR variable is between XAR and the next neighboring vertex and the next neighboring variable. And in fact, we can prove that in this definition of the Coulomb gas integral F beta, we can show that F beta satisfies the second order PDE. And this second order PDE is the same as what we described for the pure partition function, and the parameter here kappa equals 8. And F beta also satisfies the conformal covariance. And here is the same as before, and with the parameter kappa equals 8. And moreover, we can also prove that this F beta is positive. So in fact, this is a highly non-trivial fact from the definition. So here, although we choose the integrand to be positive on this interval, but there's no reason to believe that the whole integration is still positive. So in fact, this is very non-trivial fact to prove that indeed, after this choice of the integrand, the resulting integral is indeed positive. And recall that because we want to eventually relate F beta to a probability, it is very important to show that it is positive. And finally, we observe that this F beta satisfies the following asymptotic, and this asymptotic is where it is very different from the case of kappa less than 8. So here is the asymptotic. So we first describe the usual case. The usual case is that when the two neighboring points are already paired together in this boundary condition, and when the 2 points gets very close, we believe that this function will shrink to the n-1 to the probability for the n-1 interfaces. So here, this is consistent with our expectation. So after we normalize it correctly, it will converge to beta, but remove this pair of the points. And now it become a function with 2n-2 variables. And the interesting part comes with another one. So when these 2 points are not paired together, when kappa is smaller than 8, and if we choose the same normalization as the correct one, we know that when we normalize the pair of the points when they are not paired together, the limiting will be 0. However, this is no longer true when kappa equals 8. So when kappa equals 8, if we normalize the same normalization, the function will explode. In fact, we can prove that the correct normalization is this polynomial times a log factor. And after we normalize it correctly, then this function will have a finite limit. And the finite limit is still in this system of Coulomb gas integrals. And here we write this notation. This is called the tying operation. Of the boundary condition. So roughly speaking, it is a operation like this. So suppose J Suppose J and J plus 1 are not paired together in beta, and this tying operation means that we remove these 2 points and we connect the partners of these 2 points together. So this is called the tying operation. Okay, so here are the properties we derived for this explicit Coulomb gas integrals. And in fact, this collection of Coulomb gas integral doesn't first appear in our article in the physics literatures. So here I list the incomplete list in the physics literatures has already a similar description. So the description says something like that. So if we think about the uniform spanning tree, the corresponding conformal field theory has a central charge -2, and the corresponding conformal field theory is not a minimal model, and the field has a log correction. But of course, I'm not a physicist, so in fact, I do not fully understand what do this physicist literature means. But what we proved in our paper is that at least we give a rigorous result on what do they mean by the field has a log correction. Okay. Now let's go back to how we prove this formula. In fact, I hope I have already said that in order to prove this such crossing probability, the most difficult part is to figure out a proper observable for the uniform spanning tree. So in fact, what we proved precisely is the following. If we consider the uniform spanning tree in polygon with alternating boundary condition beta, and we consider the piano curve eta I starting from xi. Then we can derive that explicitly what is the limiting of this curve. The limiting curve is a Lawler chain with the following driving function. So here is the interesting part. So it is a square root of this is the same part as SLE8. And then here is the drift term. The drift term is given by partial I log the Coulomb gas integral. So in order to derive this precise limit of the piano curve, we need to figure out a proper observable. So for the observables, here I summarize on what happens to the observables for the uniform spanning tree. When n equals 1, in fact, this is the earliest result about the Gaussian boundary condition. And for that one, Lawler, Schramm, and Werner proved in their work that they construct the observable and they derive the limiting law from their observable. Later in the lecture notes by Bernoulli, Coulomb, and Smirnov, they construct a different observable but related. And both observable will give the same answer. In joint work with my postdoc and my students, Han Yong and Liu Mingchang, we generalize this observable to n equals 2. So here is the topological rectangle case. And in the earlier work by Dubeta, so in fact, he also proposed a possible observable for general polygon, but with beta equals this one. So this is the simplest one, means that all pairs 1 is connected to 2, 3 is connected to 4, and 2 minus 1 is connected to m. So he proposed observable for this pattern. And in our work, the most difficult part is that we figure out a proper observable for general boundary condition beta. So here is one example when there are 8 marked points. So when there are 8 marked points, there are various possible boundary conditions in the outside. And for each one, in fact, we define a proper observable, and this observable tells that This is the conformal map between the polygon to a rectangle with horizontal or vertical slits. And the location of the slits will represent the different boundary conditions. So after we figure out this conformal map as observable, and the next step is to solve the driving function from the observable. And this is called standard, but still require a lot of technical work. Okay, so here is the end of my talk, and here's a list of all the related reference, all the related joint works between me and my co-authors. Okay, thank you for your attention.